Hello everyone, welcome to this video. In this video, we'll be studying about the proof for Cayley theorem for group isomorphism. In the previous videos, we have studied about this theorem which states that for every group, we have a group of permutations for which both of these groups they are isomorphic to each other. Now let's prove this thing. So for that, let's assume that the given group is represented by capital G. Now, in order to prove the result, what we need to do, we need to find some group G bar, let's call it by G bar, of permutations such that it is isomorphic to the given group G, right? So what we'll do, we are given a group G, so we will make use of this group in order to construct the group G bar, right? So how, watch carefully how we may construct this group G bar. So for that, what we are doing, we are taking some element, this small g in the group capital G, and we are defining it by a function here, right? We are calling that function to be capital T subscript g, small g, where and it is some function which is defined from G to G bar, right? It is again defined from G to G only. So it is taking the element of G and giving us back the elements of G, right? So this is a function we are defining this function when we input some element x of capital G, right? In that case, what we are doing, we are simply multiplying this G with this member x, and this is done for all such members in the group G, so right? So we are just multiplying this G, the subscript, with all the elements of the group G, right? So basically from here you can see that this T subscript small g, this represents a function from G to here, it should be G only, right? It is a function from G to G which we call permutation, right? And this permutation is obtained by multiplying all the elements x of the group G by this element small g, right? So this is a permutation. So basically what we are saying, this G bar, this is a group of such permutations, right, where this small g is some member of the group capital G. Now we need to check whether this really is a group, right, under the operation of function composition. So let's check it. So for checking the group, what we require, we first of all require the closure property. So that means if we take two elements from the group G bar, suppose we are taking two elements G and H from the group G, then for the two elements TG and TH, if we multiply them, can we have some element which is again present in G bar? That is what we wanted to check under this closure property. So let's take two elements TG and TH from G bar, right, where this small g and small h, they are taken from the capital G group, right? Now what we can do, we can solve this much portion first. So TH of x. Now what is TH of x? According to definition, it is just hx, right? And what is so now treating this as one element, now applying this function T of G onto hx, we would have G into h into x, all three in multiplication. Now what we can do, because G, capital G, that is a group, so therefore it is also associative, so therefore we can redefine this bracket here over GH. Now GH into x, so that means now treating G and H as one element from the group G, we may define this T of GH as x. So basically we started with this thing and we obtained this thing. So from here, can you say that TG into TH is equal to TGH? And basically this is what we wanted to prove, that when you multiply or compose two functions together, you would obtain again some function which is a member of G bar. So therefore we have the closure property. Next, let us see the identity for the group G bar. For the group G bar, what is the identity here? For that, let's take small e as the identity in the group small capital G, right? And then we take some element TG, then we take some element TE, we compose both of them together, right? So that we would have TGE, right, like this. Now G into E is equal to G only. Why? Because E is the identity in the group capital G, so therefore this is just G, so this is TG. So that means when you compose TG with TE, you are again getting back TG, so therefore this TE would act as identity over here. So therefore we obtain the identity of the group G bar also, right? Next we wanted to check the inverse of each of the element within this set G bar of all the permutations. So here we can clearly see the inverse of TG, it is basically TG inverse. How this is so? Because when you compose this TG with TG inverse, it would simply be T of GG inverse, and GG inverse, because in the group G, E is the identity, so therefore we have the inverse of G as G inverse, so therefore it is TE. So therefore the inverse of this is TG inverse. So therefore we have the inverse, we have the identity, we have the closure property, and because we know function composition, that is associative in nature, so we have all the properties of groups verified. So therefore this G bar forms the group of permutations under function composition. So we have constructed G bar from G. Now what we wanted to show, we wanted to show that there is some mapping from G to G bar such that it is 1 1, it is onto, and it is operation preserving. If all of these properties are there, in that case we can say this phi, this forms an isomorphism. So let's see, is it what we have? So let us define phi as the mapping from G to G bar, right? So according to our construction of this G bar, we can very easily define this mapping phi such that if you take some element small g in the group capital G, then when you apply phi onto the small g, you would have some element of this capital G, which is T of G, right? So this is our mapping. Now we wanted to prove that this mapping is 1 1, this mapping is onto, and it is operation preserving. So let's prove all three one by one. So for the first part, for 1 1, what we do, we take two elements from G bar and assume that they are equal to each other. So we assume that TG is equal to TH. So if that is so, they are also equal on the identity element. So TG when applied onto E would be the same as TH applied onto E, which is the identity of the group E, which is the identity of the group G, right? So therefore solving this we have GE, solving this we have HE according to definition, and GE is G only, HE is H only. So therefore we started with TG is equal to TH and obtained G is equal to H. So therefore we have the 1 1 property with us. Next, we wanted to see the onto property. For onto property, it is very clear that for every TG we are surely having, we would surely have this G present in capital G. So therefore, by the way of our construction, phi is onto. That means for each TG in G bar, we would have some G in capital G group such that phi of this G is equal to TG. Right? So next we wanted to check the operation preserving property. Now what does it says? This property says that if we take two elements from the group G, then what would be phi of A into B? It would be T of AB according to definition, and because of the closure property, you know, T into A, T into B, this is T of A into B, right? So therefore you could write T of AB as TA multiplied with TB. And what is TA? TA is phi A, TB, that is phi of B. So therefore we have phi of AB is equal to phi of A, phi of B. So therefore we have operation preserving property here for the mapping phi. So therefore this mapping, because it is 1 1, it is onto, and it is operation preserving, it is an isomorphism between the given group G and the group of permutations G bar, and this is what we wanted to prove here in the given theorem. So I hope you understood this theorem well. Well, that is it for this video. Thank you for watching.